Hey guys, so today we are going to do chapter 1, section 3, which is all over trigonometric functions. This is kind of one of those cornerstone sections for trigonometry. This is where we finally start talking about sine, cosine, tangent, cosecant, secant, and cotangent. It's where we start seeing how these play out with triangles and angles and everything. So this is a very note-rich section. Not that there's like a lot of notes per se, but the notes that you take in this section will follow you the rest of the way through this course. So I have shared my notes, and like I've always said, you can print them off, you can do whatever you'd like with them, but just know that while we don't do a lot of examples today, the ones that we do are important, and the notes that you have in front of you are very important as we progress on. So before we dive into these different trigonometric functions, we're going to talk about Pythagorean theorem. So Pythagoras was a famous mathematician, and he discovered that if you look at the side lengths of a triangle, of a right triangle specifically, that the side lengths coordinate with each other, meaning there's an equation that we can come up with to explain the difference in the side lengths. And that equation is the Pythagorean theorem. This a squared plus b squared equals c squared. This is a cornerstone of trigonometry. It's very important. And so what this a squared plus b squared plus c squared means is that if you look at a right triangle, and you look at sides A, B, and C, C has to be the hypotenuse. That's the only special thing, really, is that the C has to be the measure of the hypotenuse. The hypotenuse is the side that is opposite of the right angle, or the longest side. So this has to be the hypotenuse over here. The other two sides you could intermix, and it doesn't really matter because you're going to square the values and you're going to add them together. But if I square the side of A and I add to that the side of B, and it's going to equal the squared side of C. And that's a really important theorem that allows us to do a lot with trigonometry and in algebra in general. It's also from triangles that we get our distance formula. You have seen distance formula, at least in math class, because I know I talk about it, I believe in math 30, but hopefully you've seen it in, algebra 1 and other classes, or maybe even a physics class, where the distance formula is actually derived from a right triangle that you can graph, where distance squared equals x2 minus x1 quantity squared plus y2 minus y1 quantity squared. But we don't usually think about it like that. We usually think about it in terms of this distance equals the square root of all of that, because then it just makes it easier for us to think about it, because distance is always a positive measure. But when you look at it this other way, with the distance squared equals x2 minus x1 squared plus y2 minus y1 squared, hopefully you're seeing like, well, wait a second, that's the Pythagorean theorem. And it really is, where D is the side of our hypotenuse. And that's what happens if we have these points, this P and this R, and then we have this x2 comma y1 down here. Then what I'm actually doing is I'm taking the distances of these sides and I'm squaring them, I'm adding them together, and then I'm taking the square root to find the distance of the hypotenuse, which is using the Pythagorean theorem. You will never be asked to prove that or do any of that, but I wanted you to show that there really is a connection, and we actually do utilize this information in a lot of different ways. And so the Pythagorean theorem is why we have the distance formula, which is pretty cool. So let's look at these trigonometric functions. This is the meat and potatoes right here. This next little section. This is key that we grasp this. This is a very generalized graph right over here. This little circle with a line through it is called theta. And it's what we're going to use to represent the different angles as we move throughout this class. Most of the time we use theta. As you can see it on the board behind me. You'll get your own form of how you like to write it, but it's a circle that continues through the middle. And that's the angle that we're usually talking about and referencing when we are trying to find trigonometric functions and things. So we have this angle, it's drawn here and it's green. And what we're going to see is that in order to figure out the value that theta has, we can actually use this triangle that is made over here between the last arm of our angle and the x-axis. So notice that it makes this right triangle right here, and look what happens. The length of this becomes our r, or our that's our hypotenuse. So all of this is really interesting. I'm giving you a lot of this information right here, not because I expect you to regurgitate it, but because I want you to see how our trigonometric functions actually interact with each other. So if we are looking from the origin to this point P that is on our angle, on our terminal side, that's our ending side, then what we see is we can find the distance of this r right here, which is kind of our radius. We're going to see in a couple sections how really all of these triangles and things actually relate back to what we call the unit circle, or just circles in general. And this circle would start at a center and then have a radius, an r of measurement, whatever that is, depending on the size of the circle. And that's what's going on right here. We're using the distance formula, and we're using triangles and angles in order to find the measure of this radius, this lowercase r. And the measure of the radius is x squared plus y squared, and all of that quantity squared. Now, again, you are not going to have to determine or like regurgitate this information, but I want you to see the basic picture, and I want you to see what we're talking about, because we're going to be talking a lot about these different angles and how we're getting them. And sometimes we're going to talk about the theta in terms of this radius and this x and this y value. And sometimes you're going to hear me talk about it in terms of opposite over adjacent. And we need to be able to use these terminologies interchangeable. Okay. So when we talk about trigonometric functions, there are 6 basic trigonometric functions. There's sine, cosine, and tangent, and maybe you've heard of those, maybe you haven't, but those are kind of the 3 big ones that we like to think about. And then their inverse trigonometric functions are cosecant, secant, and cotangent. And so I have shown you right here below this picture, we have sine, which is written S-I-N-E, but we shorten it to S-I-N with our theta. All of our trigonometric functions have a 3-letter shortened version that we actually use. But I did write out the words so that you can see how they are pronounced and what they look like. So as you read problems, if they do spell it all the way out, you do know what they're asking you for. Most of it's pretty straightforward on why we call it, like sine is S-I-N, cosine, C-O-S, tangent, T-A-N. It's usually the first 3 letters. So sine of theta is where we take our y value of this triangle and we stick it over the radius, or the r, the length of our hypotenuse. So it's y over r. Cosine of theta is going to be x over r. Okay, notice those are different. And then tangent theta is going to be y over x. Do you need to memorize these? Yes, you are going to need to memorize these. We're going to use these the rest of the semester. And so you're going to need to have these in your arsenal. I recommend making yourself either a page of notes, like at the beginning of your notebook or somewhere towards the beginning, that you can put big information, things that you should memorize, and you should add to that. There's going to be a lot of it. For some of the tests, I will give you a formula sheet, but if I give you a formula sheet, I'm going to give you a lot of formulas that you are never going to need, because you're going to need to know which ones you actually do need to utilize. So I'm never going to give you a formula though that's like cosine of theta is r over x. I'm not going to give you something that's actually inadequate or inaccurate. But I will give you more stuff than you need, because you need to prove to me that you do know how to use the information. Okay, So sine, cosine, and tangent are the three main functions, and then their inverses are cosecant, secant, and cotangent. And I purposely wrote them the way that I did because I want you to see the connection that is made between these. Sine theta is y over r. Cosecant theta is r over y. Look what happens there. They flipped. They are inverses of each other. So if you can figure out sine of theta, then if you flip it, you know your cosecant of theta. If you know cosine of theta is x over r, flip it, and now you suddenly know the secant of theta, which is r over x. So they're really nice in that they do have inverses, and they work really nicely that way. Tangent is y over x, so cotangent is x over y. Those are important to know. Now, everything I've given you so far deals with x's, y's, and the r, or the radius of this circle that we're not really talking about yet. And that is really great. But I will be 100% honest, when I learned trigonometry, that is not the way it was presented to me. I never learned it with an x and a y and an r. I learned it with an opposite and a hypotenuse and an adjacent. And I learned about SOHCAHTOA, and maybe you've heard that term before, SOHCAHTOA, which is actually just a way to memorize these different pairings. And so I'm going to give you that information as well, even though your book doesn't actually present SOHCAHTOA for a couple more sections. Because if SOHCAHTOA is what sticks in your brain and helps you to identify these different trigonometric functions, then I'd rather you have that as a tool than be sitting here staring at this X, Y, and R stuff and be completely lost. There are going to come times where a given problem, like in a couple of examples, we're going to deal with X's, Y's, and R's, but you can still think of them as opposite, adjacent, hypotenuse in most of these cases. So I'm going to scroll down so you can see what I mean. I'm giving you the same information with SOHCAHTOA that you already have with your X, Y's, and R's. So SOHCAHTOA is just a mnemonic to help you memorize what goes with sine, what goes with cosine, and what goes with tangent. The SOH tells you how to find your sine values. So SOH, SOH, that's your sine theta, means it's your opposite over your hypotenuse. And I drew a basic triangle over here, your right triangle, so you can see what I mean. Theta is down here in the bottom right hand corner. So we're trying to find the trigonometric functions in terms of theta, and theta is down there. The opposite side is the one that is opposite of theta. The adjacent side is right next to theta, and the hypotenuse is the hypotenuse. So that's where these letters are coming into play. So if I'm looking at this, then sine of theta is saying that it's O and H. So it's opposite over hypotenuse, O over H. We'll look back up here on this original graph that I have drawn up here with the green, with the R, Y, and X. If theta is down here, then the R, Y, and X would be that opposite is the Y value and R is the H value. So it's exactly the same stuff. It's just presented in a different manner. Okay. I can remember SOHCAHTOA. I don't always remember Y over R or X over R. Sometimes I have to go back and reference it, and that's okay to do. SOHCAHTOA, I never have to go back and reference. So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse, and tangent of theta is opposite over adjacent. And then their inverses, you flip them. So secant or cosecant is hypotenuse over opposite, secant is hypotenuse over adjacent, and cotangent is adjacent over opposite. So again, these different pairings are giving you the exact same information. It's just presented slightly differently. Okay. We will use the X's, Y's, and R's. We will use the opposite, adjacents, and hypotenuse. I will probably use the SOHCAHTOA method a lot more, but you are more than welcome to use whichever method clicks for you. And that's why I'm presenting you with both methods. So let's actually do a problem. And I'll leave both of these this information up on the shared screen. And I've written the problem that we're going to do up here on the whiteboard. Yes, I know that there's some glaring, and I'm sorry about that. If I turn all the lights off because it's kind of cloudy today, it gets really dark in here. So hopefully there's not enough glare to make it too big of a problem. So we are asked to find the 6 trigonometric function values for this given triangle. And it gives us a triangle. It gives us a right triangle, and it tells us that theta is down here in this lower left-hand corner, and that we have 8, 15, and 17. And so from this, we are asked to find our sine and our cosine, and our tangent, our cosecant, secant, and cotangent. Now, if you're actually trying to memorize these and what these values are, it might be helpful for you to write, okay, well, sine is going to be the y over the r. And maybe you want to write that out every time we're trying to find one, so that you know exactly where we got these numbers and you understand, and it's going to stick more. Okay, sine is y over r, cosine is x over r. Like, we can do that. I'm not going to do that. You are more than welcome to do that. Okay. So, and I will try for this first problem specifically to use the x and y's and the opposite and stuff, so you can see how they relate. But if theta is down here, and I'm trying to find the sine of theta, sine is the y over the r, or the opposite over the hypotenuse. So the opposite over the hypotenuse would be 15 over 17, which is the y over the r. So sine in this case is 15 over 17. That's all you're doing. Don't make it harder than it actually is. Now, you do always want to make sure that your fractions are simplified, but 15 and 17 don't have anything in common. But that's really all you're doing. We are just identifying what this value is, and most of the time it is a fraction. So cosine then is x over r, so that would be 8 over 17. That's adjacent over hypotenuse. Then we go down to tangent. Tangent is going to be y over x, or opposite over adjacent. So that's 15 over 8. And there we did half the problem already. Now, the nice thing is that each of these has an inverse. So sine is the inverse of cosecant. So cosecant, we just flip it. It's 17 over 15. If you wanted to actually look at it and look back at the original one, the cosecant is the r over the y. R over the y, which is what we have. Cosine correlates with our secant. So if cosine was 8 over 17, then this is 17 over 8. And tangent correlates with cotangent. So if tangent was 15 over 8, then we now have 8 over 15 for our cotangent. That is how we identify the 6 trigonometric functions for a given triangle. So hopefully these problems aren't too hard. The next one sounds hard, I think, or looks harder, but really isn't harder. And I can't really show it to you because it gives away some of the answers. So I'll have to just scroll you down. Okay. So here it gives us a different situation. Here it says the terminal side of an angle theta in standard position. Standard position means that we start from here, from our x-axis, and we move counterclockwise around our circle. We talked about this back in 1.1. So we have standard position that goes around. And so if it's in standard position, that's what it's going to mean. It says that we have in standard position passing through. Actually, I can show you. Hold on. Don't cheat. Don't cheat. I can show you by covering up the picture like that. There we go. Standard position of the angle theta passing through the point -3, 4, find the 6 trigonometric functions. So what I want you to see is it's giving us a lot of information, and it may look confusing, but really the most important part is this point, this -3, -4. We're going to plot that on our Cartesian coordinate system. So I go to the left 3 and I go down 4, and I'm going to plot this point right here. So my angle for theta is going to run through that on standard position. So what that means is I have my resting side here, and then my, oh, you can't really see that. I was hoping the green would work, but it is not dark enough. So I'll try and make it bold and big. We have our angle starting here. This is our resting side along the x-axis. But then theta is an angle, and we have our terminal side that's going to whip around until it passes through this point of -3, -4. So that means theta is all of this. That is theta. And you're like, okay, great. I don't see a triangle. Well, hopefully you will, because we can make a triangle bloop, 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 just by drawing that line right there, where our x value then is 3, and it's actually -3, and our y value, we went down -4, and then we have this r value over here that we don't know right now. And there's our r value. So we actually do have a right triangle right here. Boop, boop. Do we see this? I hope we see this. Okay. Now, we got to figure out what r is, though. We can't do any of our trigonometric functions if we don't know what r is. And this is one of the things that I gave you up above. And I told you you wouldn't have to prove it, and you don't have to prove it, but you are going to have to use that distance formula from above in order to figure out what r is. So if we scroll back up in the notes, look right here. It said r equals the square root of x squared plus y squared. We're going to use that. I'll write it right here. R equals the square root of x squared plus y squared. We're going to use that information in order to figure out what this distance is. Now, maybe some of you have had a trig class in the past, and you recognize that this is actually kind of a special triangle, because there are a few special triangles. That's totally fine. I'm still going to show it with this information because not all the triangles you encounter are special. It just so happens this one is. So that was just in case you recognize this as a special triangle. So let's figure out what r is. R equals x squared. Well, what is x? X is -3. -3 squared will give me a +9 plus y squared, which is -4. -4 times -4 will give me a +16. So we have a square root of 25. Which gives me a +5. Now, some of you might be saying, well, wait a second, when we take the square root of a number, there's a positive and a negative. And you are absolutely correct. I'm so glad you remember that from college algebra. But when we talk about distances, we don't talk about negative distances like that. So we're going to think of it just in terms of the positive number. So in this case, our r is 5. So we have -3, -4, and then our r is a +5. Now we have all of that information, and we can take care of our sine, cosine, tangent, cosecant, secant, and cotangent. Because sine is, does anybody remember? Say it aloud at home. Sine is your y over r. Well, my y is -4, and my r is a +5. So we have -4 over 5. And since I know that's my sine, I know the inverse of that is going to be my cosecant. So I'm going to flip it. -5 over 4. Yes, I did write the negative out front or connected to the top value. That's just standard kind of procedure for algebra, that we don't generally leave the negative in the denominator if the top is positive. So in general, you can just write that negative out front if you would like. Cosine then is x over r. That's -3/5. And then cosine correlates to secant. So I'm going to flip that to -5/3. And then our last one is our tangent. And our tangent is y over x. Y over x. So -4 over -3. But those are both negative. So that's just 4/3. Make sure that you pay attention to that when you do have a double negative situation that does happen. But since I know that tangent is 4/3, I can just flip that. And now I know that cotangent is 3/4. Okay. Not too bad. I wish I had a different colored marker so that you could see it a little bit better. But standard position, you have your resting side here along your x-axis, your terminal arm of your angle will come out, and it will tell you that it's going to run through a certain point, or it's going to tell you that it's going to be made up of a line, and that's what we're going to see next. I'm going to slide you back down this way, and I'll have to erase our original problem. But we are going to do one more, and then we just have the remainder of the notes. So there's just one more example that I wanted to cover, which is when we have, which I used SP as standard position just to kind of shorten my notes a tiny bit. So when you see that, that's what that means. It says that we have the terminal side of, or find the 6 trig functions of theta in standard position if the terminal side is defined by x plus 2y equals 0, where x is greater than or equal to 0. So that's a different situation because we have a line given to us as a definition of our terminal side instead of a point. And so we're like, okay, well, that's kind of weird. And it is, but it's not going to be hard because what we're going to do is we're going to find a point. In the last example over here, they told us a point, -3, 4. This time we're just going to compute out a point is what we're going to end up doing. Okay, they give us an equation. They give us this x plus 2y equals 0. That's what they give us. And they tell us that x has to be greater than or equal to 0. Okay, so pick a point. Pick a point where x is greater than or equal to 0. I'm going to let x equal 2. Okay, so let x equal 2. If x equals 2, let's figure out what y equals at that point, and then we have our point that we need so that we can draw a picture just like we just did over here for the previous problem. So if x equals 2, I plug that in, and then I'm going to solve for y. Subtract the 2 over, divide both sides by 2, and I get y equals a -1. I kind of knew that it was going to work that way, which is why I picked 2. You might not have done that and just picked 1, or you could have even picked 0 and you would get something different, and that's okay. I don't think 0 would help you all that much because you just have 0, 0, and that's not going to give you a terminal side. But anyways, we have an ordered pair now. We have the point 2, -1. So on our Cartesian coordinate system, we can draw that and figure out what our theta looks like. Okay. Coordinate system, 1, 2, 3, 1, 2, 3. Standard position means that our angle starts here on, and then it's going to shoot around until it hits the point 2, -1. So 2, -1 lies right here. That's where our terminal side is going to go through. So do be careful. Our angle, our theta, is not in here. Our theta is all of this that wraps around right there. Okay, it's the wraparound. So be careful about that, because you might be like, oh, well, it's in there. It's not, though. That's not what we're using. But we are going to use this point. I'm going to make this little tick mark smaller to make our triangle. Just like we did in the previous problem, I'm going to make my triangle from the point going up to my x-axis, because that gives me a right triangle right here. Okay, and then my x value, well, my x value was 2. My y value was -1, and then I don't know what my r is. So once again, I'm going to have to figure out what my r is. So r was the square root of x squared plus y squared. In this case, my x was 2, so 2 squared is 4, and my y is -1. -1 times -1 is a +1. So I have the square root of 5. Let me go ahead and tell you, leave it like that. Do not give a decimal representation. You will have to grow in your abilities, or maybe you don't. Maybe you're really good with your radicals. You got to get comfortable with radicals in this class. We're going to see them a lot. So in this case, my r is radical 5, not radical r. Is radical 5. Now that I have all of that information, I can come up with my sine, cosine, tangent, and all the rest of them. So I'm going to erase this, because it does ask for the 6 trig functions. Let me angle you down a little bit, slide you over, because you don't really need to see that first bit. You just need to see the picture. So we need to find sine theta, cosine theta, tangent theta, cosecant theta, secant theta, and cotangent theta. Okay, and maybe by this point now you're finally getting a handle of what each of these equals. So sine theta equals y over r. So our y in this case was -1, and our r is radical 5. Now, there's a rule in algebra and in math class that we don't ever want to leave radicals in the denominator. We have to rationalize our denominator and get those out. And the way that we do that is we multiply the denominator by itself. And when we multiply the radical 5 by radical 5, what happens is we get radical 25, which is just 5. So that's what we're going to have to do in order to get rid of that radical 5 in the denominator. So we have to multiply top and bottom by radical 5, meaning we have negative radical 5 all over 5 is the value for sine theta. And that is 100% accurate and completely good. But you don't want to leave it as -1 over radical 5. This is not simplified. This is not complete. You want to take it out here to negative radical 5 over 5. So be aware of that. Okay, cosine is x over r. So that's 2 over radical 5. Again, we're going to do the exact same process to rationalize that denominator. Top and bottom get multiplied by radical 5, leaving us with 2 radical 5 over 5 as our cosine. Kind of a side note, in case you want an extra hint on how to remember that sine is y over r and cosine is x over r. X and y, x is alphabetically before y in the alphabet, and so is cosine in terms of sine. C comes before s, and so maybe that helps make a little connection. Maybe not, but maybe it will help you. For tangent, we have y over x. So we have y over x, which is -1 over 2. We don't have to do anything with that bad boy. We're good to go. Okay, now we just flip them. But here's something that I want you to notice. We're not going to flip for sine theta. We're not going to come out here and flip the negative radical 5 over 5, because if we flip that, that puts the radical in the denominator, then we have to rationalize it again. So don't do that. Go to the very front. We have negative 1 over radical 5. Let's flip that, because that'll leave us with radical 5 over negative 1. There's no radical in the denominator, so we don't have to worry about that. It's just negative radical 5 is our cosecant. So you don't always have to come out here to the fully simplified before you do your flipping. Same thing's true for secant. I'm going to take the 2 over radical 5, flip that, and that becomes my radical 5 over 2. And I'm done. I don't have to do anything else. Cotangent, I take my tangent, which was negative 1/2, and I'm going to flip it, so it's negative 2 over 1, which is negative 2. Now I have found my 6 trigonometric functions for this given theta. And the pictures in here, my notes, I think are probably a little bit better than on the board because I have different colors and you can kind of see it all laid out there. Okay. The last page of these notes is really just reference, and it's really just for you. It's talking about quadrantal angles. That's kind of a weird word. I'm probably going to mess it up a lot. What it is these are the angles where theta is 90 and 180 and 270 and 360. They're kind of special because they lie on your axes. And so when you have to find theta when it lies on one of those axes, this is how you would do it. I will be 100% honest with you. Whenever I took trigonometry, my high school teacher made us memorize the table that you will see in just a minute. And we had to regurgitate it in under a minute or we didn't get to pass. And so I'm not going to be that mean to you. I've told you I will probably give you a formulas page on some of the tests. But if you want to be able to move through your problems quicker, this table is very important. So I would totally put the table on your page of reference notes, or even spend the time and memorize it. Will it take some time and effort? Sure. It's going to save you a lot of time though as we're working through the problems, because if you know off the top of your head that sine of 90 is 1 and you don't have to do any computations for that, that problem's going to go so much faster, because that's going to pop up over and over again as you move throughout the semester. So just so you know, I'm not going to make you memorize it. It's very good if you do though. So over here on the left is just the Cartesian coordinate system with these different points where they lie on the X and Y axes. And then it tells you what the X would be in these given situations. So when we're up here at 90 degrees, your X is 0, but your Y is 1. And so your radius is 1. And when you're over here at 180, your X is -1 and your Y is 0 and your radius is 1, and so on and so forth. We're using the radius of 1 because that's going to come up later with our unit circle, and so we're just using that. But what it tells us is the sine of 90 is 1, the cosine of 90 is 0, the tangent of 90 is undefined, and so on and so forth. Like I just show that right here. This table is where I show you 0, 90, 180, 270, and 360. Please note that if theta is 0 or if theta is 360, that's the exact same spot on your plane. It's just you've gone full circle. And so it shows you the sine values for all of those, the cosine values, the tangent, and all the whole shebang. If you memorize this table, your problems will go quicker. But again, you are not going to have to. I know in some of your homework problems, though, it does ask you to fill in certain sections or columns or rows of this table because it is that important. So while I'm not going to give you any problems right now off of this page, this table from this page is very important and worth your time and effort either to memorize or to write it down. But that is actually the end of 1.3.